Folks, this is video number 11 in the playlist that's devoted to motion design in 3D Experience release 2025x. And the problem I'm going to be doing is actually a dynamics problem. Keep in mind that there are two playlists for motion design. One of them is dynamics, the other one is kinematics. This belongs to the dynamics playlist. The problem that I'm going to do is a single degree of freedom system that is the vibration of that disk, which is hanging, let's say, from ceiling with a rod. Now, this can be viewed in vibrations courses. This is solved as a single degree of freedom system, where this bar that you see here is replaced with a torsional spring with the stiffness that you see here on the right-hand side. And of course, then we are dealing with essentially a lumped rotational mass with polar moment of inertia that's given here. And right. So the shaft here is replaced with a helical spring, as you see. And essentially the stiffness is given by the expression that you see on the right-hand side. Now, when you write the sum of all the moment equal to mass times acceleration in a rotational sense, this is what you're going to get. The only moment is what you see up there, and the mass times acceleration is replaced with mass moment of inertia times the angular acceleration. Now, this can be written in the form on the right-hand side. And in vibrations books courses, you see that this vibrates as essentially a free vibration, assuming there's no damping here, by the way. And the frequency of that vibration is square root of k over j, which, if you plug in these values, you're going to get that. Now, the actual position, the angular position of the disk is given by a sinusoidal motion that you see here, which depends on the initial condition and initial velocity. So the problem I'm going to model is these dimensions for the rod, these dimensions for the disk, and this mass of 100.25 kilogram is based on a density of steel, assuming that this is made out of steel, a density of steel which is 7,770 in the database for the 3D Experience. I'm going to do this problem twice, one without any damping and then with damping, and we'll look at the results. Now, if there is no damping, the natural frequency comes out to be 9.644, and the period of oscillation of this disk is 0.652 seconds. If there is damping present, then there's a slight change here, and yeah. So what you see is down below. Okay. So we're going to solve both of these problems. Now, I'm going to do this thing for two conditions. One of them is suppose that the disk is initially twisted by 10 degrees and let go. So basically, we have the angle of twist of the disk, and angular velocity of the disk was released from rest condition. And if this is what you see here is a MathCAD worksheet. So for the data that I showed you a minute ago, what we're going to get, these numbers that I gave you are calculated based on this data sheet. So these things, which were shown in the previous slide, are coming from a calculation from a straightforward vibration set of formulas. Now, this problem was also done with a mechanical systems experience in a different playlist, and it's right here. But remember, we're using motion design application, which is not the same as motion. It's not the same as mechanical systems experience. There was, by the way, a mistake here when it came to actually my slides in this video tutorial. Inadvertently, my slide I put down that the disk is, let me go back here. This is 10.8 millimeter. It should have been 108 millimeter. In fact, that was used, 108 millimeter was used in the, when I modeled the computer, but anyway, this is corrected thing. And incidentally, there are other ways of doing this problem, and what I'm going to do is a little bit different from what's done here, because in that tutorial, what I did, I created two parts, the disk and the base, and the base is going to be stationary, and there's a revolute joint between these two, the base and the disk. I'm not going to model the base here. All I do is to model the disk, and I show you how you go about creating that essentially base. All right, so let's go ahead there. Let me insert my first part. Insert 3D part. There's not going to be only one part, and that's going to be that disk. Okay. Give it a minute. Okay, let me call this thing properties. Let me call it disk. And here's the instance thing, also disk. Okay, let's go ahead and make it. All it is a cylinder, basically. So on that plane, I sketch. Let me draw the section of the disk. So this radius is going to be 195 millimeter, if I'm not mistaken. Let's check it out. Let's see, 195 millimeter, and the height of it is 54 times 2, which is 108. So let me go here, exit, and I'm going to pad this thing, but I'm going to pad it symmetrically, 54 up and 54 down, which is going to give you, here's a symmetry condition. So 54 up and 54 down, which is 108 millimeter. Good. Now, because I did not specify, will not specify any material properties on this, when it goes to motion design, automatically it uses properties of steel. So that's what I'm going to do. I'm done here. Notice that I'm not doing anything about the base, and there's a reason that I'm not modeling the base, because I want to show you that it's not necessary. Let's see why. So let me switch to motion design, right? It says that this is going to be the name of the mechanism. Do you want me to create it? The answer is yes, because basically there's nothing there. So this is fine. And we say, okay, and notice what happens here. Just bear with me for a second. All right. First of all, gravity is imposed downward. Now, I'm not imposing gravity in this problem. So there's a couple of things I can do. I can go here and I say deactivate this. So I go to global gravity, either make gravity 0 or say just deactivate. That's fine. So it's deactivated. There are no joints, obviously. There is a single body that I created called disk. And notice that there is also a ground. There's also a ground. Ground is created by default, and essentially it's a stationary ground or inertial frame of reference. So if I double click on this disk, if I double click on this disk, what you see here, it says the mass is 100.245 kilogram, because it is using the properties of C. Now I can overwrite that by putting my own mass. I don't want to do that, but if I do overwrite, make sure you put the proper correct IXX, IYY, etc. But this is fine. There's nothing wrong with it. This is the value of the mass of the disk, and this is what I want. So we say fine. Now the other thing is that notice that there are two markers here, one for the disk and one for the body, for the ground. The one for the ground and the one for the body these markers are always by default created at the origin of the part. The origin of my disk is exactly the origin of the ground. And in fact, you can see that if I go and move this thing, if I go and move this thing, there's going to be two uh, reference frame, not reference frame, two markers sitting on top of each other. There are two markers sitting on top of each other. Okay. In fact, you can see if I hide, for example, the one for the body, if I hide it, there's still going to be another one, but that one is for the ground. If I hide this thing, they're both going to be gone. If I bring this thing back, here is the marker for the disk, and here is the marker for the ground. Sitting on top of each other. Good. That's pretty much it. So we're going to create all the joints ourselves. Okay, all the joints ourselves. Now, what are the joints that we have? Well, first of all, we have to fix something, and we're going to fix. Even if I don't fix the ground, this ground is definitely fixed. So I'm not going to even bother fixing this ground. I'll leave it the way it is. So this is going to be automatic. You see that? There's an anchor there. So it's unnecessary to fix this thing. In the previous in that other playlist that I solved the problem with mechanical system experience, I had to fix the base, okay? Because the base was different from the ground. There was the ground automatically created by the software. There was the base that I created, and then there was a disk. Here, I don't have to do that. This is already fixed. Good. Now let's go and create our Revolut joint. So we go to mechanism. Here are the joints, and I'm going to choose the Revolut joint. And notice that the Revolut joint, it requires two. I can do that with selecting the markers. So this Revolut joint is between this marker, which is the ground, and this marker, which is the ground. Which is the disk. Okay. Let's see. Say. Okay, so that second. And there is thinking. First, I selected the ground marker, and then the second one here. Okay, this one, that one is for the ground, and this one is for the body. Okay. And then you say, okay. All right, very good. Now, what I'm going to do is I'm going to give it initial condition because I want this thing to be turned around, twisted by 10 degrees. So what I do is I go to the initial conditions. Okay. I'm going to do it by joints. I'm going to do it by joints. Here is the joints. It says, where is the joint? The joint was created here, Revolut joint. And it is position and velocity. Okay. Now, if I do position and velocity, I can specify the velocity of the release. But since I don't want that, it's going to be 0. Let me just do position. Okay, position. And position is going to be 10 degrees, right? So 10 degrees. Right there. Oops. 10 degrees. I don't have to worry about velocity because it's released from rest. It's going to be automatically 0. Now notice what happens when I say, okay, nothing will happen here. Nothing will happen here. However, when I go and click on initial state solve, you'll see that this will turn and there will be a 10-degree deviation between the two markers. Just watch right now, they're sitting on top of each other. When I say initial solve, you see that? It moved, and now there's a 10-degree deviation here. If you want to see it more, I can go and make it 50 degrees so that you can see it better, but that's okay. So these are not sitting on top of each other. That causes a revolute joint, but the disk has turned by 10 degrees, and then we're going to run it. Now, first of all, notice that immediately a dynamic step has been created. When I went into the motion design, immediately it was created. You double click on it, 5 seconds, okay? Now, let me remind you that if we have a spring with no damping, the period comes out to be 0.652. So let me do it over, let's say, 1 second. Well, I'm not going to do that over 5 seconds. I'm going to do it in 1 second. And I say, okay. And this is a dynamic, it's not kinematic, so that's good. Now, I need my spring. How do I do my spring? But the springs are under machine elements. You click on the spring, and you want a torsional spring right there. See that torsional spring? Okay. It says, where are the springs? Well, I can use markers to do that. So the spring is between the two markers, this marker and that marker. Okay. And this is fine. And the stiffness of it is 176. No damping. 176. Let's make sure that it is correct. Yeah, 176.7. Fine. 0.7. There is no damping, but if there is a damping, you just put it in, expand this thing and put a value of damping there. But right now, 0 is fine. Just leave it the way it is. Okay. And it is unloaded, so that's okay. All right. And that's pretty much it. So let's go ahead to simulation and run it. Wait until it says succeeded. Select your result file, dynamic step 1. Go to results. You can do the animation. So just give it time. So for roughly, I think 1 second, look at this is going to turn. Okay, good. There's not much you can see here, but now let's go and plot the for example, the 2D plot. Get a 2D plot. Let's see what we want here. Of what? Of the revolute and rotation. Give me the plot right there. You see that? Starts at 10 degrees, and then it goes up and it comes down. So after roughly 0.65 seconds, it repeats itself. So it gave me correct period right there. And I'm gonna do damping in a minute, but I want to show you something here. This is fine, so let's close that. Let me go to the dynamic step right here. This is a little bit jagged, so if you want to eliminate that jaggedness, go to the setting. Don't do it over every 20 cycles per second. Do it, let's see, over 100 cycles. So this is actually capturing more data as it's computing it. And let's run it and look at the same plot. So let's go ahead and run it. Simulation. Leave this thing open because it automatically updates it. There, you see that? All the jaggedness is gone. Same values, except that there's no jaggedness here. Now, what I'm going to put the damping in. So we go to, where was that thing? To machine element. There's a torsional spring. And go to damping of 5 appropriate units. Okay, so let's go run it. Leave this thing the way it is. Run it. Don't close it because then you have to do it again. Finished. Let's look at the result. Now you can see that. And look at the damping. Starts at 10 degrees. And then this is where it repeats itself, is 0.667-ish. 0.667-ish. 0.664, something like that. Anyway, you get the picture. 0.66, 0.66. 66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0.66. 0 notice that I did not fix anything because I did my spring between the ground, which is automatically fixed, and the marker for the disc. I think I wanted to do everything, but just in case, if you want to simulate this thing over a longer period of time, double click on it, and let's say we go to maybe 3 seconds. Run it. There, you can see there's a lot of damping gear. All right. Good luck.